So my name is Florian Auernhammer. I'm a research staff member in the IBM Research Lab in Zurich. And I'm going to give an overview of the new XIV architecture that we introduced for the Power 9 processor. So XIV is our new interrupt virtualization architecture. So as a background, as everyone almost has already pointed out in their talks, basically the ease of use for OpenCAPI and so on is also because you're able to use it directly out of your user space. And over time, we really have introduced I/O MMUs or adopted the memory virtualization in all pieces of our microprocessor. So we have introduced first the PCI Express I/O MMUs, then we had Nest MMUs for our network interface and the Torrent chip that was used for Power 7, and then Power 8 saw the coherent attached accelerator interfaces with CAP. And that made it easy to really move data from devices into OS space, into user space, I mean, wherever you want it. And this is also critical because you want to have the isolation that it provides for enterprise consolidated enterprise data centers as well as the cloud infrastructure, so that you can run multiple virtual machines. They are isolated from each other, and you don't have to worry about data getting into the wrong places and so on. The problem with it is that most data that you're moving in the system also at some point needs to have a notification, because you want to tell the receiver of the data that, hey, there's some new data that you have to process, which is true both for I/O data that is coming in where you need to process a network packet, but it's also true for APIs where some other processor posted somewhere some work that needs to be done, and then he wants to do an API interrupt to notify the other processor that he now has to work on it. But so far, the interrupt subsystem, that was the only piece in the microprocessor that basically did not have any virtualization support. So everything basically went through the hypervisor. In the Power architecture, we were using what we called the Power v2 interrupt architecture. So it was introduced with Power 5. Back then, we had a maximum system size of 256 threads. So coming to Power 8, we had 6 times more threads. And basically, at this time, we really had full adoption of I/O virtualization. And this led to the fact that we really ran into the capacity limit of the v2 architecture. For Power 9, there was then the desire to also have the on-chip accelerators like the NX unit that we provide and introduce on Power 8 Plus, on Power 7 Plus, and as well as OpenCAPI adapters being able to use a lot of additional interrupt sources. At the same time, in the interrupt v2 architecture, because it was already a bit dated, there is 2 restrictions, I would say, which is that on the one hand, from a hardware perspective, if you create an interrupt request, you need to represent the interrupt if it cannot be presented to a core right away. Basically, if all the cores in the system are already working for an interrupt, or if they're running at a higher priority so that you cannot deliver the interrupt, it was up to the source to represent the interrupt so that it got accepted and being processed. So that added complexity to the individual interrupt sources. Also, all the interrupts were delivered through the hypervisor, and the hypervisor was then also doing rerouting if required. So if the hypervisor determined it's better to serve that interrupt somewhere else, or it needs to be served somewhere else, it was up to the hypervisor to reroute it, which has the advantage that you can virtualize the interrupt, so you can hand virtualized interrupt information to the operating system. But at the same time, it, of course, adds significant overhead because you have to add the context switches to branch into the hypervisor and then back into the operating system. So the number of sources we could have extended rather easily, just increasing the source IDs and so on throughout our system. But really, as we saw the trend towards full and basically, virtualization being adopted in all parts of the microprocessor, especially also in our accelerators, we thought that the v2 architecture is not adequate to support all of that any longer. So we introduced an entirely new external interrupt architecture, which is called the External Interrupt Virtualization Engine Architecture, XIVE. And the main characteristics are really addressing the issues that I just presented. So we wanted to have the support for a very large number of interrupt sources and very simple attach of those sources. So the requester of an interrupt, he shouldn't have to care about can the interrupt currently be presented or whatever. He should just make the interrupt request and being done with it. At the same time, we really wanted to enable the interrupt delivery to the full to all the virtualization layers, so that you could really send the interrupts directly to an OS or even to a user, and avoid all those context switches that were associated before with branching into the hypervisor, which actually implies that you have to route your interrupt correctly, because if you want to avoid the context switch and you don't route it correctly, you're sending it potentially to the wrong target. So some key concepts that we introduced for the XIV architecture were that on the one hand, we introduced multiple levels of coalescing. So you have configuration freedom so that you can coalesce in a lot of places the interrupt presentation, so that you can optimize really the available processing resources, and that you minimize the context switches that you need for serving the interrupts. We log the interrupts on event queues, which is a very proven concept in basically all I/O virtualization. And this basically allows us to have a really large amount of interrupt sources that target a single server. So basically, with this architecture, we can handle more interrupts than on an entire P8 system by a single server in priority. We can enable the virtualization down to the user level, because the queuing concept basically is proven and has been the enabler to really do full I/O virtualization. And actually, it also removes the need to retry interrupts for the sources, because we can always log interrupt information onto the event queues and basically then process it when a processing resource becomes available. A key concept for that is for the interrupt delivery to the different virtualization layers is that we are now routing the interrupts to virtual processors or group of virtual processors, and no longer to specific logical cores or physical cores. And the and therefore, by routing to virtual processors, we take into account the actual scheduling state in the system. So if a virtual processor is currently not running, we are not presenting the interrupt, but if a virtual processor is changing its location in the system because it's scheduled on a different logical core, we will basically follow with the interrupt presentation just by targeting always the virtual processor and not a physical core. We memory map the hardware-software interface as a MMIO into the MMIO space, and that allows actually to have a flexible implementation. If you have pending interrupts, which means that there are event queues with interrupts locked on it that haven't been processed, and we can't find a processor to serve them right now, we have a backlog structure to remember later on that we still have to process a certain event queues. And actually, what we introduced also is that there is now a possibility to create escalation interrupts, what we call it. So if we don't find a server, we basically have the option to let the hypervisor define if he wants to get an interrupt created that will tell the hypervisor that there was an interrupt that couldn't be delivered, so that he can actually take care of scheduling the virtual processor that wasn't found at the point that the interrupt came in. So this is the high-level picture of the interrupt architecture, and actually we divided it into a virtualization layer and into a presentation layer. So on the individual interrupt sources, be it IPI interrupts, graphics cards, network adapters, or your network, they trigger their individual interrupt sources, and in the source layer we coalesce the interrupts so that we only present one specific interrupt source at a time in the system. Then we look up routing information, and we virtualize the interrupt information. So we replace the physical source information by a virtual source information that we can give to the OS, which we can then keep constant, independent, whether we do live migration or whatever. The operating system will always see the exact same information for the interrupt, even if the physical source is completely different. And using the routing information, we go into the report layer. The report layer logs the interrupt onto an event queue and then does a notification. And the notification uses this virtual processor-based interrupt routing. So it really gives just the information, I want to target that virtual processor or that group of virtual processors with the interrupt. So that we are able to now route the interrupt, we have in the presentation layer these thread interrupt management areas. And there is one thread interrupt management area per logical core. And in this area, the software always keeps the hardware up to date with which virtual processor is currently running. So if they change operating systems or if they disable the hypervisor on a core, they basically tell this through this TMA to the hardware. So therefore, when we route an interrupt, we get the target information from the notification information in the routing layer, and then we check, can we deliver the interrupt? Do we find the target or do we not find the target? If we find the target, we have registers here that will present the interrupt to the core. And if we don't find the target, we have the option to backlog the interrupt. So we have a backlog structure so that later on when the VP is rescheduled, we will bring back the information that we couldn't present interrupts and present them later on. And we have the option to escalate, so to notify the next higher virtualization layer. And the good thing about this new routing concept is that basically this side here, once you have set up your interrupt sources and you have set up your virtual processors that you're running, this and all of those structures involved in this process here are static. They are not changing. The only thing that is changing is the information about which virtual processors are currently running. So there is really only the information in the TMAS that needs to be changed to adapt the routing dynamically. So for the virtual processors, this is also commonly known as vCPUs. We have a range of indexes that we can use, and basically for the hypervisors, so that he still has the capability to route interrupts based on their physical location, we predefine a certain range, what we call the hard range, which is a small range of virtual processors that are really tied to the specific logical core in the with its position in the system. So on which chip is it running, which logical core on that chip. And all of the rest of this range can then be freely distributed to virtual processors, which can be attached to the hypervisor, what we call the hypervisor pool, or the operating system. So you can kind of create additional routings for the hypervisor using these pools, or you can, for each virtual processor of an operating system, you hand out a virtual processor there in one group, and basically all the virtual processors in such a group would then be tied to the same virtual machine. And then we can target either a specific virtual processor, which is commonly done in the Linux case. So typically there the routing is typically just routing interrupts to one dedicated virtual processor. But you can also route interrupts to group of virtual processors. You can say, for example, here I don't care which physical thread in the system services the interrupt, I just want to get one. And then the hardware will do some load balancing and find the one that currently is running at the lowest priority and so on. So this is really then allowing load balancing for interrupts that don't have strict affinity. And yeah, as I mentioned, for one virtual machine, the virtual processors need to be consecutive and in a power of 2 range so that we can more easily do the grouping mechanism. But basically, the number of virtual processors in such a range can be sparse. You don't need to use all virtual processors. You just need to make sure that all of those VPs in one range really belong to the same virtual machine. And actually what you can also do is that you nest interrupts. So for example, on the hypervisor hard level, you could say, I have one group that targets any physical threat on one chip, and then if I don't find anyone that can currently service my interrupt, I can escalate and interrupt all the physical threats in the system. So just to be able to more quickly adapt to scheduling needs. In addition to that, okay. No. We extend the mechanism to actually also be able to deliver interrupts to a user. And a user can be scheduled by the operating system. So it's up to the operating system where it wants to schedule a user process. Therefore, when we target an interrupt at a user level, typically what we do is we basically check across all the virtual processors belonging to the operating system if we can find this specific user process currently running. So now this is the main hardware-software interface. I want to dive a bit deeper into the threat interrupt management area. So this is really the main interface where the software tells the hardware what is currently running so that we can do the routing correctly. And it's also the interface from the hardware to the software where the hardware can present the interrupts to the software. So therefore we have 4 quad words. So one for user context, one for OS, and then one for hypervisor pool and hypervisor hard. And these registers are mapped into 3 different pages in the MMO space. So one page is used for mapping it into user space, which really just contains the first double word so that the user can accept an interrupt. The next page is used for mapping the double words 0 to 2 into the OS space so that the OS can handle OS interrupts and manage a user running and potentially put in an interrupt for the user. And then the third page is used for the hypervisor, and he has access to everything. And to facilitate the mechanism, actually those 3 MMO pages are exactly the same in terms of real addresses, independent of on which core you're making the access. So the hardware will map the access to the TMAR based on the location of the logical core that is doing the access. So if I have an operating system that was running on one core here and was accepting an interrupt, if it's running now here, it needs to target the exact same real address, which means that we don't need to remap the pages that we gave out into OS or user space. So this basically means that we don't have any overhead independent of where we are scheduling the virtual processor. We never have to remap the pages. And actually it also simplifies or gives us the implementation options to either implement this TMAR within the core or also in a central unit on the chip, because it's up to the hardware to really take in the requests and just map it to the right TMAR location. So for setting up the virtual processors, basically we have here the odd and double words where we have valid bits which enable the routing for the different type of context. So you have a valid bit here on the hypervisor hard level, which just enables the hard virtual processor. Then you have valid bits on the OS and hypervisor pool level with a value where you can specify which virtual processor is currently running. And then you have a valid bit with a user index that where you can specify which user is currently running under the OS. And when context is scheduled, you basically first put in the even double word information, which contains the scheduling state from the last time it was running. And then you enable the valid bit, which means that at this point you're now accepting new interrupts. And when you unschedule a context, you're doing it in the inverse way. So you first disable the valid bit so that you're no longer accepting interrupts. And then you're reading the even double word to take out the current state of the interrupt, so at which priority it's running and so on, so that you can then put it later in again when you reschedule. So like this, you don't lose any scheduling state, and it's really, the preemption is really seamless from the operating system perspective. Now when we receive an interrupt request, we basically in hardware check if a valid bit is on, and then we compare the virtual processor information with the interrupt request that comes in. And for the user level, actually we are comparing the operating system virtual processor information plus the user information, if both match, so that we can determine if we're really having a match for that OS, for that user thread within the operating system. So now the presentation of the interrupts in the XIV architecture is similar to what we had in the previous architecture. So we have a set of registers that the software reads, and we can present the interrupts on the three levels. Basically the hypervisor, which is merging interrupts that are pending for the pool or for the heart. We have OS level interrupts, and then we can target user level interrupts using the event-based branch facility in the Power processor. So that really allows us to make a branch into a user level interrupt routine. And an interrupt pending, a pending interrupt really means in this case that there is a valid element on an event queue. So therefore, when we have an interrupt and the interrupt is accepted, the software will go to an event queue, read an element from there to understand which source triggered an interrupt. And therefore, there is information that the hardware provides to the software to doing that. So we have here our main interrupt state bits, which are the NSR, CPPR, and PIPR. So CPPR, that's what we already had before. That's the current processor priority. The PIPR is also known from before. That's the pending interrupt priority. And now in addition, we have the NSR, which basically tells us on which level is the interrupt. So is it a VP directed interrupt, or is it a group directed interrupt, and at which level is the group? So if I have multiple group sizes, it also indicates to which kind of group it was the interrupt was sent, so that the software can determine from that which event queue does it have to go to. So from a teamer perspective, when we get an interrupt and we determined by the virtual processor information that we have an interrupt that is targeting the one specific context, we're basically checking the priority of the new interrupt against the priority of the currently pending interrupt. So if there is a pending interrupt, otherwise the PIPR is equivalent to the CPPR. And if we determine that the new interrupt has higher priority, then we basically accept the new interrupt, we update the NSR information, and we update the PIPR information to reflect the interrupt priority of the new interrupt. It could happen that there is already an interrupt pending, and in that case we then send or backlog the information that there was currently an interrupt pending and the priority at which that was. If you have a hit, but the new interrupt does not have higher priority than the current interrupt, then we directly return the information that this interrupt has to be backlogged. From a software perspective, so once we have accepted an interrupt, there's a wire basically to the core that goes up, and it will trigger the core to branch into the interrupt handler routine. And then the software will come back and read the NSR plus the CPPR registers. So the NSR, as I said, for determining which, is it a VP-based interrupt or is it a group interrupt? And actually for the CPPR, when we receive such a load operation, we atomically move the PIPR value into the CPPR, which means that we are increasing the priority the core is running at, and return that information, which means this is the new information, the new priority that the core is running at. In the prior interrupt architecture, it was actually the same, the inverse, but it wasn't necessary to do it. And like this, we can just provide all the information that we need in one operation. And then the handler will process the interrupt, and once it's done, it basically comes back and signal an int done operation just by resetting the CPPR to the old value. And then the interrupt logic can get in new interrupts at higher priorities and also process the interrupts that it sent to the backlog. So relating back to the initial layered structure of the interrupt architecture, so we have three main memory structures for delivering interrupts, which are called the event state buffer, the event assignment structure, and the event notification descriptor. So on a per source basis, we have a state buffer, which is a 2-bit state machine that coalesces interrupts just for that specific source. And we have an event assignment structure, which translates the physical source information into virtual source information and points to an event notification descriptor. And the event notification descriptor, that one is really containing the information about where is the event queue in memory, where I need to log the information about the interrupt. So we are going to write the virtualized interrupt source information from the EAS onto the event queue. We do a notification and try to find the virtual processor running in a teamer somewhere. When we find the potential target, we raise the interrupt wire to the core. And basically, that involves the interrupt handler. The interrupt handler does the interrupt acknowledge to get the information about the interrupt, handles the interrupt, and does an EOI, an event of interrupt operation to the state buffer to rearm the interrupt presentation for that source, and does a done operation to the teamer to re-enable the presentation of lower priority interrupts. So that's the basic presentation flow if we find the source and everything is nice. So what can happen is we don't find the source, so then we have a fourth structure here, which is the notification virtual target structure, which has backlog information. So there we then log the information that we couldn't deliver a specific interrupt at a certain priority. So there is actually one structure of that for each virtual processor in the system. And then it is configurable if we want to escalate, and that one has also a state buffer associated with it, so that we just escalate once, even if you get multiple interrupts that have multiple misses in the system. And then this is just a pointer to another END on another level. As I already said, when a context is scheduled, we push the information into the teamer. We first we re-enable the escalation, so the state machine here that coalesces the escalation is reset so that we have a seamless transition when we unschedule, so that when we unschedule, basically immediately have the escalation path enabled. So there's a seamless takeover between scheduling and non-scheduling phase. And actually then the hardware pulls pending interrupts out of the backlog structure. So this is done in hardware. So if there was an interrupt in the meantime that came in and that was backlogged, we're pulling that information out of the NVT once the virtual processor is rescheduled. For group interrupts, as we're presenting them one by one, this is basically a constant mechanism. So as long as there is an interrupt in the backlog, so there we are really keeping count of how many group interrupts are still outstanding. We're pulling them out of the backlog one by one because we can have multiple threads that pull them out of the backlog. So we can really distribute them then to all the threads at the same time. And on unschedule, we basically pull out the information out of the teamer. And there's a special case when, as already mentioned, an interrupt was pending and it needs to be pushed out, and it's a group interrupt. We actually do a redistribution, which means that we try to right away find another server that can take it. Just because that server couldn't process it anymore, it might be that there's another server available. And this really then goes into this holistic interrupt delivery picture. And basically, we have the same flow on the user, OS, and hypervisor level. And the EAS, that one has the routing information and really allows us to route any interrupt in the system to any level of the virtualization layer. And we can route any interrupt to any target because the event state buffers, they are mapped with one dedicated page into the MMIO space. So we can really have a fully virtualized acceptance of anyone using any interrupt source. The ENDs are fully configurable, so there's no tying interrupt ENDs to certain levels. The user level actually does not have a backlog. That's mainly for scalability, because it's difficult to scale something on the user level where we don't know how many users does one virtual machine have versus another one. So that's difficult in hardware. But basically, the escalation element serves the same purpose in this case. And then you can also have different configurations here between the escalation of the OS to the hypervisor, where you can say, skip the escalation at all, and we don't influence our scheduling on the hypervisor level. You can escalate without a notification, so basically just tell the hypervisor so that during the next scheduling phase he takes into account that an OS missed an interrupt, or does do the notification to the hypervisor so that he can take immediate action to reschedule an operating system that had a miss. So to summarize, we have introduced the new external interrupt virtualization engine architecture for the Power 9 processor, and that's the first implementation that we have there. It's the first interrupt architecture in the industry that provides full virtualization support, and thereby we eliminate a lot of context switches that are associated with a typical interrupt delivery in the previous interrupt architectures. We also minimize the overhead of the hardware-software interaction, and especially by also routing correctly in the first place. So there is, on the one hand, little overhead in moving virtual processors, but we also don't generate additional work because we had routed the interrupt wrongly in the first place. And finally, there's a high degree of configuration freedom that we provide to the hypervisor in terms of how he wants to route the interrupt, how he wants to coalescing, and how he wants to set up the escalation. And with that, I'm finishing my talk. Thank you.